Okay, cool. Um, any questions? Just before we go on, move on. I saw that there was one question which said, Kunal asked, in what condition do we do p-value test? But like Cecilia answered, we don't really do a p-value test. The p-value is a result of any statistical test that you're on. So there are like, we will talk about like the t-test, the ANOVA, or the chi-square test, or there are several more tests, but we are only looking at three of them today. And the result from these, the output from these, usually you get the p-value. And based on that p-value, you decide to either reject or accept your null hypothesis. So this is the usual like pipeline or the workflow for when you do any, for when you do, yeah, get your data, do statistical analysis, and say anything, any statement that is, new and that is not known. Okay, so different questions call for different statistical tests. So we will first look at the t-test. So what is it? So it's most commonly known as students' t-test, and it's actually a very simple tool, and you will see it in R as well, which with just a few lines of code even. And this helps you to figure out if the difference you see between two groups is actually real and it's not just fluke, caused by random luck in your data. Like if you say, like, in the beginning, I showed you the example of silver rings having a benefit in my, I don't know, mental health or whatever. If that is true, like you actually compare people who won a silver ring versus people who haven't won a silver ring, and yeah, then you compare and see if the means really differ. And I mean, there are a lot more things. Silver ring is not the best example, but yeah, so you check if the means, the two means really differ. And to do this, it also compares two things, which is the size of the difference between the means, the size of the means, and the variation or the spread of the values within the group. So this value, of course, varies a lot from this particular value, and it also varies from the mean itself. And this mean, like this is a group tested with, say, drug red, and this is a group tested with drug yellow, and there is a difference between the drug red versus the drug yellow. And this is the most basic test, and because the basic thing in most data sets is finding out the mean, because you have all your data and you get the average, and then you compare these two averages. And if the difference is large compared to the natural variation, so you have a population and then you're only sampling a little bit of that population, right? And if the difference is completely, if there is a large difference, it suggests that the groups likely differ in the real world and not just in your sample. And the t-test produces a p-value. So like I said earlier, to answer, I think was it Kunal? Yeah, Kunal's question. Yeah, so the t-test, this test also produces a p-value that helps you judge the strength of the evidence. So this is the main like logic behind what a t-test is. Is this clear? Do you have any questions? Okay, one thumbs up. Two, nice. Okay, good. Okay, so this is the most basic. You're comparing means. Just remember that when you think about t-test. Now, there are different types of t-tests, and I think it's very well explained with this example. So the first is called a one sample t-test. So again, like, you're comparing from a reference value. You're comparing the group, the mean of a group from a reference value. Say you say that people in India are of the height, the average height is 5'5" or 5'3" or something, and you're comparing that average to a reference of people in the world, So this compare for this kind of a comparison, one could use a one sample t-test. And then there is the independent sample t-test, which calls for if there are, like I said earlier, the previous example, the drug, the yellow drug kind of an example, are the means of the two independent groups are different. So it's the same t-test that we've been talking about. It just goes with another additional term in front of it as one sample or independent. So don't get confused or carried on with what each of these types mean. It's just an extension, and it's just to understand, because sometimes in your code, a one sample t-test can have a slightly different code form, like the code itself can be slightly different as compared to like a paired sample t-test sometimes. So it is important to understand what exactly you want to look at and what you want to do. Like the paired sample t-test looks at the difference between to check if there is a mean difference between two time points different from zero. So these kind of things, you use these different um, t-tests. Okay. Oh, I had two different examples. Who knew? Okay. Yeah, I think I wanted to go with this, but I think, yeah, I think this is more clearer actually, because like the global part. So say, a chocolate factory, says that the average weight of a chocolate bar is say 50 grams. Okay. And yeah, sometimes you can accept that. You can say, yeah, it is 50 grams. But some on a random day, you measured your chocolate bar and you're like, hey, wait, they say it's 50, but actually it's 48. This is not fair. But maybe it was just your chocolate bar. But how do you prove the factory and, sue them and get your money or whatever? You sample from the chocolate factory, you weigh. I mean, they have done only 30 chocolate bars. It's not a good sample size. Do not do that if you're trying to sue them. Go for a higher sample size. But yeah, you can sample like a number from the factory and look for their mean and say the mean is 48. Let's a value as compared to what they claim, which is a 50. Then you can compare the two. And if the difference is significant, then you can say that, hey, yeah, I can sue this chocolate factory because they are lying to us. This is not the truth. So this is one way, and that falls under this one sample t-test. Another one, which, like I said, the drug red versus drug green, and if there's a difference, yeah, that falls on the independent t-test. And the time part, the pair t-test usually follows either a before and an after pattern. So before a drug and after a drug. Say before a drug, your weight was whatever, X kilograms. And after a drug, it has changed in these particular ways. And you can compare the same population. When you're comparing the same population, it falls under a paired t-test. So, like I said earlier, this is an extension of it. This is not to confuse you because usually you think about it once you have your data forms and you know that you want to compare the means, but then what kind of means are you comparing? Is it global versus what you measure? Is it two different populations, independent t-test? Or is it the same population but different time points? So some things to remember as we move on. Any questions so far?
Just as a peek preview, in the R code later, we will only do independent t-test, like the examples, because yeah, it's one of the most common, but that's also true that there's the pair t-test is like same population over time. But in R, you can
Use the
you
same
don't need
code.
this distinction. So we will have
Okay.
examples with independent t-test, and then you can think of your own data, and we can have a
Yeah.
look of
Yeah.
other examples.
Yeah. Yeah, I didn't know this about R, but I remember using MATLAB, another programming language which you can use to analyze your data. And I remember that for each of the different t-tests, you use a different function. So, I mean, yeah, today we're using R, and maybe you continue using R for the rest of your career, or maybe not. Maybe you have a change in your programming language because, say, MATLAB or Python or something else is preferential for you. And it's just good to know always how you're analyzing your data, because yes, today the program does it for you, but like we have this, we have access to a program that, the machine just does it. But I mean, initially when these tests were discovered, they were all done by hand or with calculators. And it is always good to know like what kind of data you're looking at.
And
Okay,
also what the machine does behind the
yes,
hood,
true.
because you really need, because it's true, in R you have only one function, which is handy, you just have to remember
Mhm.
one, but what you put, like the values you put inside the parentheses, describe then if
Mm,
it's a one sample test, a parity test, and this is important then to know like
yeah,
data set, what kind of data do you have, what are you looking for, and
yeah,
etc.
yeah, yeah. Okay, if we don't have more questions, we can move on. And like I said earlier, like how do you interpret t-test results? So like, you enter the code and then the R gives you a bunch of values, like, it gives you what is called an output. It spits out this output. And usually the output has the mean difference. And that is the mean, like the difference, because you're comparing two averages, you're comparing two means, you have the mean difference as well. And then a p-value. And always, here is where your decision rule comes with the p-value. If p-value is lower than 0.05, what do? You reject the null hypothesis and accept the alternative hypothesis. So the t-test tells us whether the difference in average is real or if it is just random. This is the most basic test. Okay, so let's move on. Any questions in these tests so far? We can move on to ANOVA, right? Yes. Okay, cool. So ANOVA, well, it's the short form is for analysis of variance. Here, of course, it sounds exactly like, testing two means. It sounds exactly like t-test. When there is t-test, why do you need to do ANOVA? That's usually the question that comes up. But with ANOVA, it's a little bit more powerful because you can also compare the differences, the means of more than two groups. So you have drug A, B, C, D, you can compare the means of all of those things. And oftentimes, like I did this in my experiments, for example, where I tested my animals with three kinds of drugs, and I also had a control where it was I just gave them some water or like just a solution, just to see like if they reacted normally, if they reacted to just water on that particular day. And on such things, it's really useful to say, yeah, that there was a difference between the control versus two of these other groups, and so on. Like here, there are four different material parts, and they're looking at the mean of strength, and yeah, and that each of these means have different values, and you can compare, yeah, different, like more than two groups. That's the whole point of it. Again, there are two types of ANOVA, the one-factor ANOVA and the two-factor ANOVA. And oftentimes, one looks at this with the different categories or like how they're classified as this into these different groups. For example, one-factor ANOVA tests whether there is a difference between the mean of more than two groups. So like say this group, say, you testing medicine, you're testing some like a drug, you're testing a drug. And well, you give one group, you say that, okay, let them, just meditate. They're using their brains, let them just meditate, no drug given. Second group, you give them a drug, okay, and say what is the benefit on their health. And the third group, you say, okay, no medicine, no meditation, but let them do some yoga, and let's see if there is an improvement in their flexibility or something. So when there is more than two groups, that's the most simplest one, which is the one-factor ANOVA. Okay. And the second one, which is the two-factor ANOVA, is slightly complicated because you're looking at two variables or two factors. For example, you're comparing you have two factors which play an equal role in the decision or in the hypothesis that you have framed. For example, you're looking at say your hypothesis is men and women okay, men earn more than women if they have I don't know, if they've completed their PhD, random statement, yeah. And so here there are two factors you're looking at. One is gender, and the second is the highest level of education. So maybe some of them have completed PhD, some of them completed bachelor's, BSc, master's, whatever, your high school, anything. And you're also looking at both these factors directing at their income, right? So their salary. So when two factors feed into question that you're looking at, then you use a two-factor ANOVA. Like another example, like type of therapy. So of course you can do meditation, you can do give a drug, you can do yoga, but you're also looking at the gender that could also have an effect on how it is on women versus how it is on men, right? On say something like heart disease or something, right? So again, two factors playing a role. Similarly, maybe someone can type in here what it could be for these three things. It's the field of study, university, and say time spent. What do you think? How could these two factors play in, like for you to use an two-factor ANOVA? Can someone suggest it? Anybody? Is it clear though? If it is not clear, I can go over it. Maybe university type, private, and government, okay? And why is there a second factor, field of study? And like, what do you expect from this kind of a thing where you're looking at two factors playing into a question of, say, hours spent?
Maybe to clarify, are you looking for an answer like a claim or a statement or
Like a claim, yeah, like or
yeah,
a statement of what your question can be rather.
what your question can be? All
What
right.
is your question? Like, I mean, you're given this random data set with two
Yeah.
variables, like field of study and university are your two variables. And then you have another column, okay, which is your result, which is hours spent, for
What could
example.
you
So what
investigate?
could your
Mm-hmm.
question be?
Mm-hmm.
So
Mm-hmm.
it's thinking in the opposite direction, because usually you come up with a question and then you collect the data and you do the statistical analysis, but this is the other way around.
Yeah, this could
Science
be.
study from private universities get high paying job. No, I think we are looking at just these three things. So maybe I can type in here. So variable one is field of study. So this could be whatever, science, history, whatever. And variable two.
Yeah, I think the question could be, but it's just that we're looking at the last example that has the time. How is it called?
Yeah,
Sand
yeah,
filling.
the
Yeah,
sand timer. Yeah,
yeah. So if there was a dollar sign, yes. Like how
yes,
is the
yeah.
field of study and the university type influence salary? Yes. It's
Mm-hmm.
just now we are looking at something like related to time. Social science PhD take longer to finish. Yes, you're missing the other variable though, which is the university type. It could be social science PhD from a private university take longer to finish, something like
Yeah,
that.
yeah, yeah,
Or yeah,
yeah. Yeah, I think that's a good answer. I think Chichi, you gave the answer. Yeah, so if you, yeah, social science or science study at whatever university, government institution takes longer or takes shorter. Social science PhDs from government universities takes longer. Yes, that's a good example. That's true. Masters. Yeah. Yes. To put it the other way around. I mean, this could be your, again, this is your statement. What could your question be? Like, how would you frame this as a question if you flip it? Yeah, that is one. Yeah, that's true. That's good. Okay.
Yeah, exactly. I immediately went to how fast you are to finish, but it could also be hours spent in the
Yeah, in
library.
the library. True.
Yeah,
Yeah.
hours spent commuting
Yeah.
could also be.
Mm-hmm.
Maybe private universities are more central,
Mm.
and so, and I don't know,
Mm-hmm.
historically, maybe some field of studies are more in the city center, and
Mm-hmm.
some others are
Mm-hmm.
more far away. So could be also hours spent in the bus. I don't know.
Mm-hmm. Yeah.
Yeah,
Yeah. Yeah.
could be really
Yeah.
anything.
Yeah. I mean, it's just to play around with what kind of variables you can have in your data set and like what kind of questions can you form with these different variables. It's just yeah, it's just a way to frame your questions and your statements and the claims that you eventually make. Okay, let's move on. Again, ANOVA, it's a little code, like a little code chunk. We'll see it in R again. And here what you get, the output is called an F statistic. So it's very similar like to the mean value that we got at the t-test, but it's just a different value because now you're comparing different groups. The F statistic has its own mathematical formula. I didn't want to paste any formulas in my presentation today, but it has its own way of calculation. If you're interested, you could of course look it up, see how it is calculated because it's also interesting in its own way. And from the F statistic, of course, the p-value is calculated. And once again, you make the decision rule with the p-value, which is if it's lesser than 0.05, you reject the null hypothesis. And the ANOVA, to kind of summarize it, asks the question if there are differences between groups. If are the differences between groups bigger than the variation within groups? So this is one of the question that it also asks because it looks at not just the two groups by itself or the three groups or four groups by itself, but also within the group, how is it changing? And within each of the groups, what is the difference? So that's one way to look at ANOVA. Okay. Then the third test and the last test for today is the chi-square test. And this is once again very interesting, mainly because it is based on categorical variables. So categorical variables would mean you have two categories under the category gender. Say they prefer a newspaper. It can be any preferred newspaper. It can be X number of categories for this particular variable. It could be X number of frequency. This could also change because you give it a score of 1, 2, 3, 4 daily. You name it. You label it. You have classified it under a certain form of a category. And again, highest education level. Again, you are making the category. You are giving the category label. So this could even be primary education, also could be a education, like this is the highest education level, but it could also be anything else. So the definition goes that the chi-square test is a hypothesis test used for categorical variables with nominal or ordinal measurement value, which would mean that you could have like what is already there, like X number of categories, or you give it an ordinal, you give it a value, you assign it a value of 1, 2, 3, 4. So that becomes an ordinal measurement scale. And the chi-square test checks whether the frequencies, oh, I'm sorry, the frequencies occurring in the sample differ significantly from the frequencies that one would expect. So, which is that if the observed frequencies are compared with the expected frequencies and the deviations are usually examined, which is to say that before you go on to collect your data, sometimes it could be that sometimes you from previous literature, right? You could say that drug X performs in this particular way, and you have the frequencies for this drug X, and you compare that with what you have got with your experiments, what you have expected, what you have observed. And usually this comparison between the expected and the observed falls under a chi-square test. Is this clear? So when do you use a chi-square test? You usually use it when your data are counts, like I said, ordinal. So 1, 2, 3, 4, you have like a score. For example, in my data, I measured how animals are aggressive, So I had sometimes a whole count that I created for myself where, one was, the lowest aggressive, two was mid aggressive, three was slightly more, and four was heavily aggressive. So you can make your count, your score as that, your category. So you can use when the data are categories, like I showed, gender or this preferred newspaper, and the kind of data that you can put in a table format. So what you saw until now, like the ANOVA and the t-test, yeah, you do put your data in a table format, but most often they are just counts and you get a mean of it and you're comparing just the means with each other. But here you're comparing the frequency. So you're also comparing how the data is within itself and comparing it within itself and also to other data. And you do not use when the data is continuous or when the data are averages. For that, you use the t-test or the ANOVA or any other test that comes up. So what is the workflow of this? For example, like you are you're doing a survey somewhere and you get these two categories of data, like the gender, male and female, and the highest level. If we categorize the continuous, will chi-test apply? There's a question. We categorize the continuous data, will
I
the
think it's the
chi-test?
same thing as the dice example before, right?
Mm-hmm.
Or age, yes.
Mm-hmm.
If we move
Yeah,
it as a factor, yes,
yeah, yeah,
that can be
yeah,
used
yeah.
as
Yes, you can. In youth,
yes.
adult, yeah. Okay, you say 20, age 20 to 30. Then it
And then
becomes,
each one of these
yeah, yeah,
values is a category. Yes,
yes,
you like
yes,
in R, you will turn it into a factor and then it will be
yeah,
treated. Yeah.
yeah, 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 yeah. Yeah, so you do a survey, and in this survey, you're just, ticking one, crossing one, whatever, And from this survey, you can put that into a tabular format using R, using Excel, whatever, right? And you have a count of things that fall in this category and things that fall in the second category. And with this, you can have a count. So everything falls into this kind of a tabular format. So you have a category. So you're comparing, how do I put it? You have two different categories by itself, and you have information from the gender category and the education level category, and each has its own value. And of course, you can have a total value as well. And yeah, to identify if there is a correlation, you do a chi-square test and you compare, yeah, like I said earlier, the observed frequency versus the minus the expected frequency and get a chi-square value as such. Any questions until now? Maybe I finish this and we can do questions.
Yeah.
So how you interpret the chi-square? So the outputs are usually the chi-square value, which is again from a formula as such. And so maybe this is your observed usually, right? And yeah, the expected could be slightly different from maybe previous literature or what you expected. Like before you started out, maybe you had an assumption with, say, sort of a binomial probability. You had an assumption that maybe there are like five females in this village who are without graduation, and you had an assumption in mind, so you compare the assumption versus what you actually observe, and with that you get the chi-square value. And with the chi-square value, one could easily calculate the p-value from it. And once again, the decision rule with the p-value applies. So if the p-value is lower than 0.05, then you reject the null hypothesis, accept the alternative hypothesis. And to summarize the chi-square test, it compares what we observe to what we expect if there were no relationship. So this is the overall summary of the chi-square test. Do you have any questions in the chi-square test? In case of T and ANOVA or chi, we can simply calculate the means and percentages and then compare, right? The difference will be visible. Then how these T or chi test add value to our results? Very good question. Really good question. Yes, you can. So,
They
I
will
mean,
most
yeah,
probably not be visible.
Mhm.
Like now we are also given like very extreme examples, right? But
Yeah,
sometimes there's no visible difference, but the test tells you if there is a statistical difference or not.
yeah,
So only like seeing the two numbers, maybe they are very close by, like 45.7
yeah,
versus 37. And you're
yeah,
like, of course,
yeah,
there's no difference. But the test can tell you if actually that those two numbers that look very close to each other are actually very like clustered.
yeah,
It could
yeah,
be. Yeah,
yeah,
sorry.
yeah, 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 yeah. And sometimes even like, um, I think there's a rule which says that, never believe your eyes sometimes, because when you plot things, sometimes that, like your bar graphs, they look like they are different, like they look like, yeah, like a 30 versus a 4. Like I had this with my own data. I am not kidding. I was comparing something that the value, the value, the mean or the average or the percentage of it was 30% of my animals did something and 40% of my animals did something else. And visually, just by looking at it and by plotting it, it looked like a clear difference, like a 30 is bigger, I mean, lesser than 45 or 40, So of course, like this group of animals is different from this group of animals. But when I did the chi-square test, because usually you also enter in your sample size, right? So it wasn't significant. So again, like, my eyes were lying to me technically when I was looking at the data. It said that, yeah, no, these two things are, they're different, it said to me. But then the chi-square test, yeah, the chi-square test, I mean, showed me the reality that no, don't believe your eyes. You believe the data, like you believe what you see, right? Not what you see, but what the data tells you, because that is the truth. Because you can easily just claim and go on about saying, yeah, I saw a difference, and this is a new finding and everything. But in reality, that's not the case. Like that's the reason that we do any of these statistical tests, and which tells us that if yeah, what we do is right or wrong. Yeah.
And I wanted to add, because we will see it when we go into R, that the opposite is also the case.
Yeah.
So, and that because you will see when we go into the code, the first thing we do always is to plot. Even before
Yeah.
looking at anything, we always plot, because it's true that you shouldn't believe the plot alone, but it's also true that you should always be able to see things like how the data is looking, because plots can also show you, for example, this example we had before with the outlier, right? If you
Yeah.
have a very strong evidence that the mean is somewhere, but then you plot it and it's like, but actually it's because there's 2 or 3 points that are so far away that pull the mean away from where it should be. So it's both things are equally true. So you can't just do a blind test without looking at your
Yeah.
data, and you shouldn't have a plot without testing your hypothesis.
Yeah. True. In case where differences are minutely visible, will the p-value be around 0.05 only? Not significant, difference will not be there. Will be there. Um,
In case
minutely invisible. Sorry, I read that wrong. Yeah, will the p-value be around 0.05? And then there will not be a significant difference. Yeah, that could also be the case. And I think that's what exactly Cecilia was explaining, where, yeah, like sometimes, yeah, your graphs, like, I mean, if your sample size is huge and, you've collected all your data and the two bar plots can look extremely similar and the p-value is 0.05, then yes, there is a difference. So there is, although it looks similar, there is a difference, like an inherent difference in the data that you can't visually see. Sorry, Ajay, you've raised your hand.
And because the p-value could be very deceptive and
Yeah.
very ambiguous sometimes, that's why we always interpret p-value in the presence of the effect size. Like we always, we just don't see always just the p-value. We also see
Yeah.
the effect size also, because sometimes the effect size is very, very minute, but it is still coming as a significant. And
Yeah.
definitely when we'll see the sessions in the R, that time we'll see the
Yeah.
interpretation of the p-value goes along with the effect size and also the confidence interval. Then
Yes.
only actually that's why in the present research, no more journals will accept or reject your paper just based upon the p-value.
Yeah.
They made it compulsory to add with the p-value, you must also submit the effect size and also submit the confidence interval. Then
Yes.
these three figures, they interpret the p-value. So,
Absolutely
because
right.
p is a very slippery concept, where to
Mm-hmm.
believe and not to believe. Because as Dr. Cecilia mentioned earlier, it is sometimes it's completely at the edge, you know.
Yeah.
So how to go with that? Uh,
Yeah. Yeah.
Thank
Yeah.
you. Just to add on, thank you.
Yes. Yes.
No,
Of
no,
course.
it's very important to
Yeah.
to to say these things also because as we said, the 005 is always it's a like somebody decided that this
Yeah.
was the cutoff, but
Yeah.
you can also have like I think we said it before, we had the example of 0.06.
Yeah.
It's not significant in the strictly statistical term, but you can confidently say that there is something there. Maybe
Yeah.
you can't
It's a
say that it's
trend.
statistically significant, but there is some effect that is not
Yeah.
excluded. So don't
Yeah.
fall into the trap of like thinking in boxes. You need, like Ajay said, you need to see how is your sample size. You need to see the effect size. You need to plot it. You need to do the test, and then you put all this information together and you craft a story of what you believe the data is telling you. And of course, science is made so that people make claims based on data and statistics, and then somebody else's can build upon their work and say, okay, I did the same experiment, I had the same conclusion, or no, I changed this thing and this was the new result. So we can easily build on each other's experiment also.
Yeah. Yes. Absolutely. Hey, if there are no any further questions, yeah, let's look at an overall summary of all the different t-test, the t-test, the ANOVA, and the chi-square, which we just went over today. So, yeah, if your data type is numerical, you either use the t-test or the ANOVA. If it is categorical, you go for the chi-square test. Number of groups. If you have just two groups, if you're comparing before and after a drug A versus drug B, t-test. If you have more than three groups, two or more than two groups, or three and more groups, the ANOVA. And again, the one factor and the two factor ANOVA that we looked into. And if the data is all categories, then it's also the chi-square test. And what are you comparing? You're comparing means in both the t-test and the ANOVA, and you're comparing counts or the frequency in the chi-square test. And the output that you usually get, the t-test value, or the mean value rather, is what the t-test output is, as in the F statistic is the ANOVA output, the chi-square value is the chi-square test value. And the degree of freedom, it depends upon the sample size of the t-test. It also depends upon the different groups and also the size. So I think Ajay mentioned it really clearly with the size, the effect effect size, which really matters, and that really depends upon the degree of freedom depends upon the size. So in t-test and ANOVA compare averages to kind of wrap it up, and the chi-square compares patterns. And this is the key message of these three different tests, which are, I would say, the start to statistical tests. These are not the only tests. There are several more tests, and how your data applies to, of course, these tests would apply to your kind of data, but for sure, like this is only the beginning. Like there's a lot, the statistical world is bigger rather. I thought I could just can you explain the degree of freedom? Sure. We can, maybe I can go back to that slide.
I'm also always super confused about the degree of freedom. I think I Google it every now and then because it's a concept that doesn't stick in my brain. I don't know why.
The same
It is
for me.
true. It is true. When I was explaining yesterday also, I mentioned especially that there are few concepts that every professor say that these are slippery. Just if you get it, okay, otherwise move on. There is a lot of things to cover up. So,
Yes. No, that
Yeah.
makes sense.
Yeah. No, also with the degree of freedom, it always feels like a very simple concept, because the rule always for the degree of freedom is n minus 1. So n is the total, values that you're looking at. Like here we looked at 3 values, so n equals 3. And the degree of freedom is usually 3 minus 1, which is 2. But it can get very confusing when it comes to categorical data, like your when you use chi-square test for your categorical data, there it becomes a bit confusing as to what your degree of freedom can be, because is it the value that is there within the table, or is it the number of rows and columns in your table? And yeah, it is always confusing, but I think the one thing to remember here is like to understand what your total is. And because every value, like if you take 10 values, 9 of those values can be anything, right? Like it can add up to anything, but the 10th value is always forced. So your degree of freedom for the sample size of 10 is the 9, is equal to 9, because 9 values have the freedom to be whatever they want, but the 10th has to fit, has to lock in, has to be locked in. It's quite an abstract concept, I think, mathematically also.
But I like the example you made with the triangle. Two of the 3 angles can be anything between 1 and 170. No, 170. Yeah,
180, 180.
Yeah, but the other one is dependent on the first 2. And once you know the first 2, that one is fixed, right?
Yeah.
And like what I tried an example that was like, let's imagine there are 20 spots to be sit by the 20 students. So when the first student will come inside the class, it has many options, nobody is there, all spots are empty. But by the time 20th student is coming to the place, he has no choice, he has no choice. He has to take the spot which is left empty. That is somewhere, the degree of freedom goes something like that. So the last value has no choice, but it has to take the last spot. And maybe there is some theoretical background behind it statistically, so why it matters in statistical analysis. And that's why most of the books of basic statistics, they just mention it, but not that much theoretically. Maybe that's it, not important for us that much. So nothing much to worry if, even if you don't understand. Many statisticians also don't know what it is, so it's okay. We can.
Yeah, that's why I also said I always get confused, and every time I Google it, no worries. And for the question, wouldn't degree of freedom necessarily be n minus 1? It is if you have one group. But if you have more than one group, it's 1 for each group, right? It's the same. The example with the class is great. If you have one class with 20 spots, the last one is always locked. So it's 19. But if you have 3 classrooms, they all depend on themselves, not on each other. Right? So it's, but again, I mean, I think we have still some time, because after this we go to R, but I will do it after the break anyway. If there's
I
no
had a
questions.
little one slide. Wait. wait, before this, I had one slide to kind of wrap everything up. Maybe I share that and then uh, we can take and then move on to the R part. Yeah. So maybe let's think about everything we learned today. So from randomness, from flipping a coin, throwing a dice, to evidence, to actually looking at what kind of statistical tests that one can use, categorical tests, or looking at different kind of averages. So let's run through it. So we saw probability, and we know that that describes uncertainty. Like there's a lot of randomness in the world, weather is weird, everything is random, but I mean, but you can still calculate the probability, and that is the coolest part about this in all of this randomness. And distributions is a bigger extension of what we understand about probability, so it describes patterns of uncertainty. When you're thinking about distributions, you're looking at random variables where you turn outcomes into numbers. You say heads is 1, tails is 0, so you're putting that into numbers, numerical ideas, concepts, not ideas, concepts. And then once you have these kind of numbers in place, once you have random variables, once you have actually thinking of numbers, with your data, you can start thinking about asking the actual questions and converting these questions into testable claims, which is what a hypothesis is. It's an educated guess. And with forming a hypothesis, you can test the hypothesis, you weigh evidence against chance, with this courtroom example several times. And then most often when you are testing a hypothesis, that's when you're collecting your data, you're actually doing your tests and all of that, and then you get p-values and the degree of freedom, you get the type of errors that you can, you have all of this in mind when you're doing this. And yeah, these measure how surprising the data is, if it's actually this boring, like if it actually goes to the null hypothesis, or if it is actually saying, no, like, the convict is actually a convict, put him to jail, it's interesting actually. And yeah, and then the statistical tests part where we saw, which are just tools for your question. So your research is the bigger part, but all of these are just tools for you to access your research, for other people to access your research more, to say it in the right words. So yeah, every data set has an uncertainty, every claim needs evidence, every decision has a risk of error. And to wrap it all up, statistics does not prove things. This is wrong. Like silver doesn't make me happy, but it measures evidence under uncertainty. So gather your data, you do your statistical tests, and then you can help make the least wrong decision possible. So you can show that, okay, maybe, wearing a silver ring doesn't. Okay, I'm not going to talk about silver, but, you can make the least wrong decision. So let's just keep it at that. Yeah, and then we can, now that we understand the logic, we can let the computer do the calculations. I think this is the most important part.
Yes.
So do we have any questions with the logic part so far, with the theory part? Because right now it's 11:20 here, so we can maybe have a 10-minute break also before we go, because
No, I
it's
think now there will be the long break before
Yes,
the
I
next
think
session, right?
this will be a 30 minutes break, and
okay.
let's meet after 30 minutes.
Okay, perfect.
Okay,
Yeah.
thank you.
Okay.
So, welcome back. We will now run the statistical test we saw in the previous lecture and see the functions associated. I have the same script from this morning open, but we can also open a new one to keep everything clean. I will remove everything so we can have a clean environment, and I can also restart everything. You don't have to, but just to be on the same place if you just open your RStudio, then we are all at the same point. All right, so the first thing we need to do, we just cleaned all our environments, so also the packages we loaded before are not longer available. So as always, we start by loading the packages we need. And since we installed it already, we will just load the tidyverse package. This we need for data manipulation and for using the ggplot function and readr and dplyr. Yes, and everything else is in base R. All right, so the first thing we're gonna see now is the t-test. For the first example, I will generate some random data and then see how to plot it and how to do the t-test. And then we will have a scenario, like I will paste a scenario in which a researcher wants to investigate a specific question, and we will see how to use that data to create our own, use that scenario to create our own data. And then we will go over some exercises, but maybe better to do the exercises at the end so we can see how we can pace ourselves and do the exercises together. And then if we have some time, I have a separate exercise sheet. But if we don't manage, which is totally fine, that is an extra exercise sheet, I will just share it with you and you can do it at your own pace, and there's the answers and everything. All right, so this morning we saw how to simulate some data. And we used for a normal distribution, we used the function rnorm. All right? Just this as a recap to remember. In this case, we want to do a t-test. So as you might remember, we want to compare two different groups. So we need to run this function 2 times. And let's say the first time we have a sample size of 100 people or whatever. And we give it a mean of 50, just again as an example, and the standard deviation of 10. So this will be our group, group A. Group A. So if we run this line, we have here, we can also use our head function to see the first few values. So head of group A. So we have some numbers that go between that are around 50 with a standard deviation of 10. And we have 100 of them. This will be our group A. Let's say now that we want a second group. We call it group B. And of course, here we are simulating data, right? We are not using an existing data set. So we are creating it our own. So we give it our own mean and standard deviation. So for sake of trying the t-test, we will use our norm of the same number. So again, 100 individuals. The mean this time will be 60, slightly higher. And the standard deviation will again be 10. These are all numbers I'm just inventing. You can also do your own numbers. For example, you can put heights or weights or distances, anything you might want to try, but this is just as an example. And so we run this and we do again head of group B. And you can see there's, in this case, 6 numbers. They're all around. The mean is this time 60 and the standard deviation is the same as before. So, as we saw before, this notation is not the best. We need to change this into a data frame. And to do that, we have our wonderful function called tibble. So I will call this data frame df. You can call it whatever you want. And we want a tibble. In this case, before we had only one column, right? We had one column with the flip coin, the dice, or whatever. But in this case, we want 2 columns because one is for the group and one is for the number we created here. All right. So we can think of this number as, I don't know, what could it be? Could be a score in a test, let's say. So this number, we will say it's a score. So this will be the name of the column. And then since we have 2 groups, we need to ask R to C, meaning combine. And inside this combine, we tell him group A and group B. So these are the 2 groups we have. Comma, I go below so you can see the nice difference. So what this code does, it takes the 100 numbers for each group and it stacks them into a vertical line. So it takes the first 100 of the group A, and then it takes the second 100 of the group B, and it puts them one on top of each other in one column called score. So takes 100 from group A, 100, not 10, values from group A, then 100 values from group B. And it puts them all in one column called score. In this case, I called it score. Then we need another column, the column that if we just leave it as it is now, we have this 100 numbers plus 100 numbers, so 200 rows, but we don't know who belongs to whom, right? So what we want is another column that says specify the group. So this is how I called it myself. I call it group. And in this case, we want to ask R to repeat. Rep is for repeat. And combine. So we need both things. We need R to repeat the group. We can call it A and B, or group A and group B. So what this does is that it creates a column called group and then repeats the value group A and group B 100 times. So there will be 100 times A and 100 times B. So if we run this, I forgot a piece of information, and R tells me. So it tells me there is an error here. There's something wrong. Because the column group, like, how many times do I have to repeat this? R doesn't necessarily know that this is 100 of group A of 100 of group B. It just knows that there's 200 values and I want them to be named in 2 different ways. But how many times? And this is, in our case, easy because we know that we put 100 numbers for the column A and 100 for the column B. So each you have to repeat, 100. So what does this piece of code do? Creates a column called group and rep the values, group A and group B, 100 times each. All right, so if I run this now, it creates my data frame, and let's have a look at it. If I open it here, I have my column score, how I called it, that has all the numbers that I created before from these two vectors. And then I have a column group, which has group A, group A, group A repeated until number 100, well, 99. And then it starts, 100. And then it starts with group B from 101 to 200. I hope this is clear. If not, let me know. But this is, again, this is how we randomize, like simulate our data, but then we have to put it in a way that ggplot understands it. So this is our way to put it in a data frame with 2 columns and all the rows. Now we can have a look at the plot. Like we can plot it and have a look, how would they look? So how we can do it, since it's R norm, so it's a normal distribution, we can do 2 bell curves, but we can put them together in the same ggplot. So let's start ggplot. We give it our data, which is the F. We give it our X and Y values this time. No, sorry, the X value, which is score. We don't want a Y, we want the frequency of how many times each value happens. But we can give it a different color, for example. So we can say, we can fill the area of the curve by group, which again is one of our columns here. So this will plot the score number on the x-axis and will fill the area of the bell curve with different colors, so we can see visually the difference. The visualization we choose is called geom density. And we can run it like this. Let's see how it is, and then maybe we can add some titles. Here it is. So as you can see, it filled with the color. So you can see group A, group B that are slightly off. So one is a bit lower because it has the mean of 50. And the other one is slightly higher because it has higher, like moved to the right side because it has the mean of 60, right? What we can do to increase a bit this visualization, maybe, it's to put an alpha. Alpha stands for like the transparency level of these bell curves. So if you put alpha 0.5, it goes from 0 to 1. 1 is completely opaque, and that's the default. And 0 is completely transparent. So we can do something in between. And if I run this again, you can see the curve underneath, right? It's just a way to visualize it a bit better, but yeah. And maybe we can add a title, and we say title comparing group A, A and B. I have to sneeze, maybe. Yes, I did have to sneeze. All right. So far, so good. It's very similar to what we saw this morning as well. What changes now is that we run the t-test. So we want to see if there is a true difference, like already from the plot, we can see that there are some differences, but we want to do a statistical test. To do that in R, very easy, simple, the function is called t-test. It's in the stats package, which is in base R. So in t-test, the t-test once again is done between two groups. So what we need to do is to give him the group A and group B. All right? If I run this, I have a very interesting output. And now we will look at it together. Are we all at the t-test part? Give me thumbs up before I go into the output. Good. If something is not clear, please let me know. All right. There is a lot going on here. So we will focus on four most important things. The first one, we learned it from today, is what? The p-value. Exactly. So you see, it's not a number, it's very convenient, right? It's a number that is like quite, I don't know if you guys are familiar with this notation. It's scientific notation for a very, very tiny number. And now you can see it, you can understand it is that you take the first digit and then you put 13 zeros before it. All right? So this will be a 0.00000, a lot of zeros, 5. So this is an incredibly tiny p-value. All right? This is way much smaller than our cutoff of 0.05. Exactly, like Kavitha wrote, it's 0.00005. It's way smaller than what we need. So what do we do when the p-value is smaller than? We reject the null hypothesis. And the null hypothesis is that there is no difference between the groups. Always, there is no difference. So we say this p-value is below the 0.05. We reject the null hypothesis. There is difference between group A and group B. So I will put 4 things to check. The first one is the p-value. P-value, very small, we reject H0, meaning there is difference between groups. All right? Then, second thing to have a look at, the estimates. So once again, this will not surprise you because this was data that we created, like fake data. So this, I'm not surprised that the mean of X is almost 50 and the mean of Y is almost 60. Why? Because that was my data creation phase. So when you will use your own data, this is a very important information that tells you, okay, the mean of X, the population X group A is 48.98. The mean of Y, which is the second population, the second group, is 60.5. So the second is the sample estimates. in our case 50 and 60, but with your own data will be maybe something that you need to take care of. Then the third thing we want to see, we saw it already, we mentioned it multiple times today, but we never really went into it, is what is it? This one. Confidence interval, 95% confidence interval. What does this number mean? This number, usually the most important thing you have to check is that the two parts of the range in an ideal world should have the same sign. So in this case, we have both of them have a minus sign. So what does it mean? It means that the true difference of these two populations lies between these points, between minus 14 and minus 8. We are confident that 95% of the population, we are 95% confident that the true difference between these two populations lies between minus 14 and minus 8. All right? If the range, so what I mean by checking the sign is that the range should not include 0. If the range includes 0, it means that you are not really sure if there is a positive or a negative difference between the two groups. For example, in this case, we know that the group A has lower mean than the group B. And there is statistically significant difference between these two. If the values were more close together and this confidence interval would encompass 0, we wouldn't have been so sure about if one was lower, if group A was, for example, as a lower average than group B. But since we have this minus sign, we can say, okay, we are confident, 90%, 95%, that group A has lower average because it's minus. We always start with the first group. The first group has lower average than the group B. All right? If it was positive, if this number would have been positive, we would have said that the group A has higher averages than group B. And this high value lies between these two numbers. I hope this is clear. If there's something missing, please let me know. The confidence interval is one of those things that is also always very important to check. And that's why when we will see a lot of outputs today and we will look at all the different things you need to check on. So first is maybe the data, just have a brief look at how they look. You plot it and then you run the test and you see the output. Yes, the confidence interval part. Yes. So this provides these two numbers are the range. So you imagine the slide we saw before with the distribution of this normal distribution. Then there was this yellow area underneath, right? And you have this range that can be between any number. And you know the confidence interval tells you the range for the difference between these two groups. So in this case, I can say the difference between group A and group B lies in any number that is between minus 14.47 and minus 8.58. So any number in this range, I'm 95% confident that is true. All right. The closer the range it is to each other, the more you are sure about your output, or the less values this output could have. the wider the range, there are many other possibilities for this outcome or for this difference to be. The really the important thing to remember is that this range should never be between before and after 0. So for example, if I had a confidence interval exactly around 0, so if I would have a 95% confidence interval of the range between -5 and +5, this means that there's like 5 points below 0 and 5 above 0. This is just an example of I could not say if the effect of the difference between the two groups is positive or negative, because it could be any number between -5 and +5. Yes.
Yes. Just to add one more point here, and someone's mic. Okay, yeah. This confidence interval value, as Dr. Cecilia is explaining, it is actually an estimate of the population value as well, that the population value fall between this lower value, the first confidence interval, and the higher value. And as Dr. Silva was saying, it should not include 0. That means you are making some mistake, or because 0, if the effect in the population is 0, it means it doesn't make any sense of any calculation. That's why in this range 0 should not fall, that we should see first thing. And these are the estimate value that because at the end what we want to estimate, that how close we are to the population value. Yes, Dr. Cecilia, right? How close we are to the population value. And the narrow the gap between this confidence interval is, the closer we are able to estimate the population value, right? So the two things, number one, there should not be 0 between this confidence interval value. Second, the gap between the lower confidence interval and the upper confidence interval, it should be as less as possible. It means that much precisely we are able to estimate the population value. That is the two things we have to estimate. And Dheeraj is actually confused that why we are not able to see these value in the plot which we created, just before that.
Yeah. Because it's a different plot.
Yeah,
it's
because
not
two different things completely. So
yes, it is confusing because we always plot and we always see somehow a bell curve, but one thing is our data. And this, for example, in the plot you see now, I hope you still see my screen. In the plot you see now in my screen, you have our data. We are not plotting the probability distribution. This is a different kind of plot, right? But the probability distribution would also look like a normal distribution, like a bell curve. And maybe I can, yeah, and these are exactly the 3 examples that Ajay was talking about. So this would be not, I wouldn't say not preferred, because it's not a question of preference. It could happen. This is just the scenario in which maybe the two populations have no real difference. But this would also be reflected by the p-value, right? You would have like multiple feedback from this. And this is, for example, similar to our example. So the true population, like Ajay said, can lie in between, the true population value can lie between, the true population difference can lie between these two numbers. And if it's -5, -15 towards -5, there is a bigger gap. But if the gap is -15 to -12, I am more sure that the real difference between population lies between these two values. So it could be, for example, minus 12.8 or minus 13, etc., etc. But there's mathematically less values between these two within this range. So I'm more sure that the true population difference lies between these two numbers. But it could be really anything. The really important thing to check is that they are both on the same direction. And it can also be on the plus sign, all right? Can be +5 to +15, all right? And it's the difference, the minus sign and the plus sign is just how you interpret those two groups. Because as I said, in this t-test, we put group A first and group B second. So we say we get out the information that group A lies, the difference is on the minus. So group A has lower averages than group B, right? But maybe we can do exactly the same exact thing. Group B and group A. And you see, it's exactly the same test. What I did here was to switch. So in the first one, I put group A first and group B second. And so the confidence interval was on the negative. If I switch it, if I use group B as the reference, it's exactly the same number, but it's on the positive side. Because in this case, I'm comparing group B, and group B it's always the first group you put in, and group B has higher values of group A. So this is something you can get from this output as additional information. But yeah, this was just an extra check to just make it a bit clearer, I hope. But if not, please let me know. All right, let's rerun the original one, this one. For example, if the interval is 2 and -2 and it has 0, then what would be the interpretation? The interpretation would be that, so we can put it this way. You are 95% sure that it lies between -2 and +2. But this means that you are not sure. In some cases could have one could be lower than the other, and in some other cases, one could be higher than the other. So group A could be, in some cases, as lower average than B, and at the same time as higher average than B. This is not really answering any of our question. This would actually mean if the confidence interval lie between 2 and -2, would mean that there's not really clear difference between the two groups. And in this case, you would have a p-value that is higher than 0.05, highly probable, because you didn't reject the null hypothesis. So the two groups might be identical or very similar, or have differences that are not statistically significant. Does that make sense? Super. All right, the fourth, no, 1, 2, 3, yes. Last thing we need to have a look at, number 4, is, I think Kavitha mentioned it as the output or the type of test. And so in the t-test, it's a t-value, t-statistics. So t-statistics, which is this beautiful number here. All right, this represents, I will put it as a function later, but we can think about it as the signal to noise ratio. So the signal is the difference between the two means. So in this case will be 60 minus 50. So it would be 10. So the t-statistic is signal to noise. The signal is mean of B minus mean of A. In this, oops, this was unequal, sorry. In our case, would be 60 minus 50 equal 10. And we divide this number by the standard deviation. Or the spread, the variation, the spread. Variation of our data. The spread of our data. So if it's 0, if this t-test is 0, again, it would mean that there's no difference because the difference between mean is exactly the same as the spread. All right? Or the variation among the data. I will paste the function later, but I also don't want to confuse it with statistics. So the thing to remember, even if you don't want to know, let's forget how it's calculated. You want to know if it's 0, if t equals 0, there's no difference between the two populations. If it's negative or positive, there is the difference between the two groups. All right. And the negative or positive sign just tell you the direction. All right. So in this case, it's minus. So it means that the first group is smaller than the second group. If it was positive, it will mean that the first group is bigger than the second group. Effect size? Sorry, what was the question?
Can we interpret it as the effect size, the t value?
The t value, I'm wondering, is it exactly the same thing? T statistics?
I mean, I think it is the one that kind of measures how far, your result is from the null hypothesis. I don't know if it can be interpreted as the effect size. I'm not sure.
Okay.
So the t statistics measure. So I'm just trying to think of a way to explain the signal to noise. It's like how.
It seems it is effect size because the signal to ratio is called as effect size.
All right. So
Okay.
maybe I didn't know this notation, but yes, effects, yeah. Because I think one would be I'm not sure. Maybe we can look it up later, but one would be the more statistical, like hardcore math, and one would be more the practical significance. And I think effect size would be more the practical way of explaining things. Yeah. But maybe we can look it up.
Yeah.
I'm
And
also not.
oftentimes, yeah, because the p-value is usually you derive it from the t statistic value. Like you can calculate the p-value from the statistical the t value rather the t-test value, and oftentimes like if it is large in the sense if it is largely away from 0, the likelihood of the p-value being small is high. So it's likely to be lesser than a 0.05. So yeah, one could call it an effect size. That's true.
And you see, in that context, the confidence interval interpretation also becomes more, sensible because the value is 0.7, which is between -8 and -14. So our effect, the sample-based effect size is -7, but in the population, we think the effect size can lie between -14 to -8.
Yeah, exactly. Yeah, you measure the strength, right? The
Strength,
effect.
yes, strength of kind.
Yeah.
Yes, exactly.
Yeah, exactly. Yeah. You can see it as the difference between because for now we just phrased it as, is there a difference, yes or no? But the t or the effect size tell you how much of a difference there is, right? And that's also related to the confidence interval. It's not only that there is or there is not, but how much of it there is, in case there is. Yeah. All right. So I am thinking if it's better to have the scenario now and then move to the ANOVA, maybe it's better. And then we leave the exercises for the end of the day, for like at the end. So if we have enough time, we can choose whichever, but then let's do a scenario. I will paste it in the chat, and then I will give you just a few minutes. You don't have to type the code. You have to think about it. How would you organize things? And then I will type it I will type the code. All right. So the scenario is this. Let me copy it here. I will read it out loud and maybe I can also put it here. Weep. This is too much. So we recruited 15 people to delete their app for a week. And we call this group the detox group. And 15 people to continue their habits as usual. And we call this regular group. We know from previous literature that anxiety has a spread or standard deviation of 5. We expect the regular group to average around 30, while we predict that the detox group will be lower, around 20. So I will give you just a couple of minutes to think about this, and then I will, how would you change these numbers here to reflect this scenario, all right? That's about it, because everything else we can copy and paste, but the only difference is how would you change the number within this function, all right? And maybe we can rename group A into detox group and group B into regular group. So I give you 2 minutes to just think about it, and then I will do it here. All right. So
you can type in what you would
yeah,
think
if you want
would change from the previous code for this particular question. Like it's very similar.
Yeah, exactly. I think I will just copy paste this. If you have an answer, you can put it in the chat already. Otherwise, I will do it here. So first of all, we rename this because group A, group B is not so easy. Okay, we have already a participant.
Super.
And my glasses. All right, I will copy your code in my R, and because it's bigger also for me, perfect. So we recruited 15 people, perfect, in group detox and in group regular. Both have 15 people, super. We know from previous literature that the standard deviation is 5, yes, for both. We expect the regular group to average around 30, super, and the detox to average around 20, super. The only problem here, and could be that it gives you an error, is that it's missing a comma. But R will definitely yell at you, so no worries about that, and typos are super normal. Perfect. So there's nothing to change. We can run this. and we have our group detox and group regular. We don't have to, but I always like to see if I did something wrong. So I want to see head of group detox, looks everything like it should be, perfect. And there is 15 numbers, yes. So now we create the table. Since I don't want to retype everything, I will just copy paste this code and change the values, all right? So for example, we don't have group A anymore, but we have group detox and group regular. By the way, it doesn't matter if you do it the opposite, if you put regular first and detox after, it will just look mirrored, but you can order them as you want. Just remember to put the right label for the right part. So this will be detox, and this will be regular. All right? This number is super important to change. We can change this maybe. We could, like, score could be still anxiety score. So yeah, we can keep it as score. And this is important. Before we had the 100 but this time we have 15, right? So we only repeated 15 times each, all right? So I will put it another name. You can overwrite it, but let's say this is the DF for the detox experiment. Okay, and now we want to ggplot it, and we give it the DF detox. We give it the statics as x equal. Yeah, we can do the same as before. And then we will also do a different plot after, just to see how we can plot things differently. But in this case, we say X is score, and we fill by group. So it's exactly the same identical plot, right? And then we say geom density, and we give it a transparency of 0.5. Yeah, this is our data set. Another way to plot this that is maybe less confusing because we will not use the Gaussian would be to use box plots. All right, this is maybe because I saw it from the slides. There were some examples with the box plot. This is also another good way to visualize. So what we can do is to say same thing. So the data frame is always the detox. The X this time will be the group because we will have on the X side the two groups. And in the Y, we will have the score. Then for this, we will use the box plot. Okay, what happens if I run this? Is that on the X-axis, I have the two groups, right? And on the Y-axis, I have the score for each. I can also do how I did it before and have two different colors. Why not? I can have the two different colors for the two different groups. I just have to add fill, like I did for the density plot. Okay? So this is one of the examples we were saying before. I think somebody was asking, yeah, but if I clearly see a difference, why do I need to do the test? This would be one of those examples, right? That you see, wow, yes, there is a difference. but still it's not enough. We need to do a t-test. How do we do the t-test? We type t.test. And in this case, we use a different kind of notation. What we can do is something we talked about before, right? The t-test function is the same, but the ways you write things inside can differentiate between the independent t-test or the pair t-test, etc., etc. So another way of writing, in this example, doesn't really matter because it's very simple data, but it's just another way of writing the same thing. We have score, which is the variable we are interested in investigating. So we want to know how much the score changes between these two groups. Tilde, group, which means, so our question is, how do we, it's group, yes. How do this group, how does score depend on the group? How does anxiety score depends on the group? This is the question we're asking. Of course, like this, it's not enough because again, we have to tell them which data we are using, right? It's the same thing as in the ggplot. First thing we have to say which is the data. And in this case, it's DF detox. The output is exactly the same. It's just a different way of writing this, all right? Before we look at the output, are we all golden? Are we all, did we lost someone in between? Give me thumbs or no thumbs. All right. So what can we say from this output? Let's look at our 4 things. First thing is the p-value. This is 0.00004. So we are, again, it's a very small number. So we reject the null hypothesis. The null hypothesis was that there is no difference between the groups. So with the p-value, we can say, yes, there is difference between the two groups. The second thing to check, again, not super important for our data, but if you have your own data, you will look at the sample estimates. The mean in the group detox is 17 point something, and the mean in the group regular is 28 point something. Then the confidence interval. Once again, we are within 2 minus, so we are between minus 16 and minus 6. So we are good. There is a negative difference. So meaning that the first group, in our case was the detox group, which is the reference group, is lower in average than the regular group. All right? And the T statistic is, again, minus 4.8. Meaning, we said if it's 0, there is no difference. So it's negative and by far. So this means that the test was successful. So there is difference and is substantial. All right? Is it all clear so far? How do we do that with R? Because next we will move to ANOVA, if there's no questions. All right, then I move to ANOVA. ANOVA, as we saw before, it's difference between more than two groups, right? Let's say 3, 4 groups. So when we have 3 or more groups and we want to know if their averages are different. It's the same as the t-test, just that we have multiple ones. A question that I get asked often is, yeah, why, for example, if I have 4 groups, why don't I run, or if I have 3 groups, why don't I run 2 t-tests between these groups? Why do I need to run an ANOVA? It's important if you have more than 2 groups to run an ANOVA because the chance, if you run 2 or 3 multiple t-tests between all the groups, all the combination of groups, the chance that you get a false positive, it's very, very high. And this means that you think that something is significant, but actually it's not. So if you do multiple t-tests between groups, you might find something significant, but it's actually not significant when you compare them all together. All right? ANOVA so keeps everything tidy and look at everything at once, and so it's more reliable. Okay, let's create our 3 groups. So we have group 1, group 2, and group 3. Once again, we use our favorite function of today, our norm. And let's say we sample 50 people that have a mean of 10, 10, and a standard deviation of 10. Crazy high. And then I copy this in its entirety. I paste it here and I just change the mean to 20. And I do it again, and I change group T to 30. So group 1 has mean of 10, group 2 has mean of 2, 20, and group 3 has mean of 30. All right? These are our 3 groups. I run all of this. We have everything in here. And we now create our table. Data. Very creative. Table. We have, I don't know, value, score, let's say value. What do we do now? We need the C, right? For combine. Oh, here, C. So we combine G1, G2, G3. Yes. And then we make a new column called group. And we repeat the combination of A, B, and C. Each, how many times? We see it from here, each 50 times. It's the exact same code we ran before to create the table, and we run it again. We have our data. We can also investigate it from here. We have the 2 columns, value and group. And everything looks correct. Perfect. Let's plot it. I know after a while it might sound tedious because we repeat and repeat and repeat, but that helps also you for having this a bit clearer and also to show you the iter. Every time you have the data, you load the data, you plot it and you see how it looks, and then you do statistics tests. So aesthetic, we have X equal group, Y equal value, and I put the Y because I want the box plot, and fill equal group because I want the nice different colors, plus geom box plot. Oops, I forgot something. What did I forget? Yes, let me see, X group, value, data. Yes, it was telling me what was the problem. Did you forget to add parentheses, as in geombox plot parentheses? Yes, I did. Here it is. All right, here it is. Our data, group A, B, and C. And as you can see, I had the mean of 10 and G is the mean, 2 as the mean of 20, so you can easily see the differences. All right, now we are ready to run the ANOVA. We have our data and we have visualized it nicely. So the function to run the ANOVA is AOV, and then we give, like we did in the last t-test value. It's the thing we are investigating if it differs by group. And we have to give the data is equal data, because I was very uncreative and I called the data frame data. The problem now is that we would like to save this output, because if I run this only, I have some sort of output, but it's not what I'm looking for. What I'm looking for is the p-value and all these other statistics that it doesn't tell me anything. Why? Because this function needs to be called with another function. So what we do is that we create an object that stores this information. We call it model, for example. And if I run this, then I can run another function called summary of this model. And this will be how I visualize my information, how R prints back the information to me. Before we look at the output, please let me know if everything if I should go slower, if something is missing, please let me know. And then we will have a look at the output. All right. Then let's have a look. So we have, in this case, again, we need to find the p-value. The p-value is stored in the last column is this PR, that is the p-value. Once again, we have this scientific notation that said that is with a number with 16 decimals before, after the point, right? 16 zeros. It's an incredibly tiny number. But also we see something new here. We see some stars. This is very, very handy because sometimes you have multiple things you want to check at the same time. And you want to see if, for example, our value is influenced by group, and this is our output, but it could be that our value is influenced by many other things and we can add them as the column in our data frame. And then what the summary function will do is that it will print all the different variables, one after the other, and it will tell you for each its own p-value. In this case, doesn't matter because we had only one, and it will give us one p-value for the difference between groups. But in the future, when that will happen, you will have many different lines like this with its own asterisks next to it. The more the asterisks, the smaller the p-value is. And it goes from a point, which is like at the edge, so at 0.05. One asterisk means that is on one decimal point, so 0.0 something, that is lower than 5, and so on and so forth. So 2 asterisk, 2, 0, and 3 asterisk is 3 or more. All right? So in this case, we know that this is extremely significant. Okay? Questions so far before I move to the rest about the output we are seeing and the fact that you have to save it as a model?
I have a question. So maybe somebody also has a very similar question. So the p-value that is generated here, the significance, it is a so this ANOVA tests all three groups, right? So all three groups are different from each other is what the
Yes.
statistic, the
output.
significance is saying, right? It's not
Yes.
group A versus group B. We haven't done the individual, what do you call it?
Yeah, the individual, yes, exactly.
Yeah.
And that's why I think that's what I meant at the beginning. You could do, for example, several t-tests and you have different outputs.
Yeah.
But the anonymous case is just giving you one output, like the groups, are they different from each other? Yes or no?
Exactly.
Yes,
Yeah.
exactly.
Yeah. And
All right.
oftentimes in journals and stuff, you would see that like the stars, the significant stars you would see on top of these bar plots. Okay, can you explain the meaning of the stars, as he says?
Yeah.
Apoor was asking.
So it's like a scientific code. Sometimes you don't want to, visually, you need an input immediately if something is significant or not, because it's like, to see this very complicated scientific notation, it's not immediately clear, right? So what R does is like to give you stars to show you how tiny the p-value is. So you have the codes down here. So if there's nothing next to it, this is not the case though. There's only one variable and we only have this one. But if this had nothing next to it, it means that it's a number of 1. So
Yeah.
it's like, or 100%. But if you go down to 0.1, there will be a dot next to this p-value. The more decimal numbers you get, the more asterisks you get. Okay? Sorry, yeah, this was like this. So the point you get if you have a 0.05, that's the cutoff. Sorry.
Yeah. 0.1, you don't get any stars, which means that it doesn't lie, it's not statistically significant or anything. Like it's not, it doesn't matter. Yeah.
Yeah, it's
There's
not
no
significant.
effect, rather.
Exactly.
Yeah. It's non-significant.
So yeah, if you have 1 0 before, it's 1 star. If you have 2, it's 2 stars. If you have anything smaller than this number, which is again a very, very small p-value, then you have a very high significance, a super high significance, because the p-value is incredibly small. Does that make more sense or not? It's just a code to see it more visually. Yeah. You
And
could,
it's often used in like journals, like where instead of like Chechi said, where instead of like, diving deep into the paper and looking for, is the p-value, like to the power of -16, you could just like look at the stars. Usually you find it on top of the graphs, and when you usually go through the figures, and that easily tells you if the data has been significant or if it's not significant. And I mean, it's just cues to maybe read a paper or read a figure. Yeah.
all right. So, any other question? I would skip a minute on the residuals because we will see them tomorrow and I don't want to confuse you too much. But the other one, so before we had the T statistics for the T test, but for the ANOVA we have the F. And again, that's again the signal to noise ratio, right? So it's by dividing the group variation divided the individual variation. So you can think of the signal and the noise as the signal is the difference you found between the groups, divided by the variation within the group. So the higher the value, the more strong is your result. And can we compare t-test and z-test? Which one is the z-test? I don't remember. Can you, if you give me a minute, I will have a look. The z-score, I think. Or the z-score, is that what we were talking about this morning, I think, right? Let me have a fast look because I'm not sure.
Yeah.
Sorry. Maybe Ajay knows, just in case.
In my view, it seems they are different things, and of course
Yeah.
you can compare any two different statistical tests, but it should make some sense, comparing them.
Yeah.
Z we do for the standardization of the variables, and here we are doing test for completely different things. So so I don't think so it will give much information if we compare both of them. But again, it depends upon what is your research objective, Maybe in some situations it may be helpful, but even I never come across this situation.
I see.
I mean, the Z test is a slightly different test than I mean, it's very similar, but slightly different than the T test. But if you're talking about the Z score, I mean, I'm reading that it's a value, right? Like that tells you how far a single value is from the
Yeah.
mean, and it's usually measured in standard deviations, whereas the T test is a statistical, like it's a test that's testing the hypothesis. And so so do you mean the Z test or the Z score? Z test, yeah. So that's a different test. And what my
I
quick,
think I think
uh,
I was also just looking it up, but I think the main difference here lies between us in these examples, we make our own data.
yeah,
And I say that the standard deviation is 10 for these data sets, but in a real world situation, I wouldn't know what's the standard deviation of a population. I have to test and I have to check it and I have to find out. I think Z-test, I think you use when you have like this kind of situation, simulated data, or you're modeling assumptions, but again, I will have to, maybe I will look it up today and come back to you tomorrow, because maybe it's what Ajay said, it's like a bit comparing apple and oranges. Yes, of course you can, but what kind of information would it give it back, right? I think that was a good way to put it. You can do anything you want. The problem is what is your assumption? What is your question? What are you trying to find out with this comparison? Because most of the time you do tests or calculations that have no meaning, and you find patterns that don't exist. Yeah, that would be my answer. But again, I will have a look at it and maybe come back tomorrow about this.
Yeah, same here. Let's check it up and bring more lights tomorrow. That's better.
Yeah. Good. All right. Then, because we don't have so much time, let's do the last. That is the chi-square. Sorry, I call it chi because that's how I learned it, but how did you say it today, Kavitha? Chi-square.
Chi-square. I mean,
Yes.
it's a Greek letter, so I think you know.
Yes, exactly. They're always super confusing. Yes. All right, but let's do that now, and then maybe if we have time, we can do an exercise or a scenario from one of the three, and you can choose which one. So, of course, because we have to have complications most of the time, in the previous test, in the t-test and the ANOVA, we were looking for differences in averages of numbers, right? Kavitha had this beautiful slide in which she showed that we are looking at the difference of means between populations. But in the chi-square test, we don't have means. We don't look at the difference in means. Instead, we have counts. So we have to look at counts and how many, for example, people fall into a specific category, right? This was very nicely put, and maybe later we will share the slides so you have it in one go. But what does it mean in R, for example, is that we have to reorganize our data differently. Because unlike the t-test or the ANOVA that use a list of numbers, a chi-square needs a table, a table with like the same number of rows and columns. And we call it this a matrix. So when it has like numbers, a fixed number of row and columns, it is called a matrix. So we create this demo matrix first, and we create it with 2 rows by 2 rows. So we need 4 numbers. So demo matrix, we will have, again, R is very convenient. It has a function for it that's called matrix. And as you can see, it asks for the number of rows, the number of columns, and this is what we can tell it. I said we want, so I will put it here, we want a matrix with 4 numbers, 2 rows and 2 columns. All right, so we use the number, I will invent the numbers here. We do 10 and we do 30, and then we do 25 and 15. You can also put everything in one row here, but I decided I put it this way so it's visually you will see how it will appear. Okay, so you have these 2 numbers and these 2 numbers, and then we want to tell the number of row. Number of row is 2. And by row, what is by row? If false, the matrix is filled by columns. Otherwise, the matrix is filled by row. In this case, I wanted to fill by row because I want the 10 and 30 filled first, 10, 30, and then 25 and 15. So I want it to look exactly how it looks in the script. So what do we say then? We say true. So we wanted the numbers to be filled first in the row, and then when it's done with the row, it goes in the second row, okay? So if I run this, we have a demo matrix, and if you open it, as you can see here, it doesn't only tell you how many, it tells you where are they positioned. So there's 2 rows with 2 columns, 2 rows and 2 columns. We can also view it here. And you can see the position. So the first number is the row number, then there is a comma, and the second number after the comma is the column. So position 1, 1 is 10. Position 2, 1 is 25, etc., etc. This I just skip because maybe this is not related to R, but it's good to know. So which one is the function to do chi-square test? It's called here it is, chi-square dot test. What do we put in here? The demo matrix. Once again, we can save it as an object or not. I will just run it as it is now. And here is our output. Again, what do we want to see? First things first, always p-value. The p-value is 0.001, which if we wanted to use the notation here would be a 1 star. Or am I wrong? Yes, I'm super wrong. It would be a 2 stars. It would be a 0.01. So this is a good value. We have a very small p-value. We reject the null hypothesis and we say that the categories are different. And then we have the x-square value. And this number is like, if we go back to the point of the observed and expected that we saw before, this number tells us how much of your observed numbers differ from the expected. So the expectation is always that they're perfectly balanced, because the expectation is always the null hypothesis that everything is the same. There's no difference. But so how much your observed value different from the expected, that will be, sorry, if the expected and the observed are identical, so if there's no difference and if everything is perfectly balanced, then this value would be 0. It's the same principle as the t statistics. If there's no difference, it's a 0. And a score far away from 0, like 995, is quite high and shows a strong signal that the 2 variables are not independent and they're not perfectly balanced. All right? Should we do a scenario with this, with the chi-square as the last 10 minutes? A scenario, and then, yes, let's do that. All right, let me see, what is my scenario? Yes. This is nice. I will copy it in the chat and I will read it. So, in this scenario, we are asking this question. Is there a link between employment type, for example, freelance versus salaried, and job satisfaction, satisfied versus not satisfied? We surveyed 100 people. The freelance group, which is 50 people, 30 are satisfied and 20 are not satisfied. The salaried group, again, another 50 people, 40 are satisfied and 10 are not satisfied. So what I want you to do now is to create this matrix with the values you think there should be in the matrix, and then run this function chi-square test with the matrix you just created. All right? 2-3 minutes, maybe even, 3 minutes, because then we have to wrap it up, I think. And then if somebody wants to copy it in the chat, otherwise I will write it myself. Nice, very fast. Okay, I will copy your code and put it in my RStudio and we will have a look, all right? So, we have the matrix of the first row is 30 and 20. Yes, those are the freelance group. So in our case, these numbers are our freelance group. And the second row of number are our salaried group. And if we look at the data in this direction, the 30 and 45 are the happy people. Sorry, the first, yes, these are the happy people, satisfied, and 20 and 10 are the very unsatisfied people. This is exactly correct. So we will run this, and then we can do, so another thing we could do that before we didn't, because it was just a demo and I didn't know how to call the variables. In this case, we know the variables, right? And if we open the matrix like this, we might forget, right? What was the satisfied group again, the first or the second? So what we might want to do is to name the columns. There is a function in R called call names, and we give it the name of the matrix. So call name, freelance, salaried, and we assign C, so repeat. Satisfied is the first one, right? Satisfied. And not satisfied. What happened now? That these two have suddenly a nice name. All right? Check on me that I did the right thing, but 30 and 40 are the satisfied. Yes. And then we also want to maybe rename the rows. The rows were the salaried and not, freelance and the salaried. So in that we call row names, not call names, but row names. And we give it again freelance, salaried. And we assign. The first was freelance. And the second was salaried. All right? And if we look at the, what is it? Here. Here. Here it is, freelance and salary. So now it's more clear. If tomorrow I open again this code, I remember everything and everything is super nice. So now I do chi-square test. of freelance salaried. All right. Let's have a look at the output. So we have a p-value that is smaller than 0.05, not by much, but enough for us. Our cutoff again is 0.05. This is smaller. We reject the null hypothesis. There is a significant link between being salaried and freelance and being satisfied. Okay, so this means that we reject the null hypothesis that there is no difference whatsoever. And we can say there is a link between the type of contract you have and being happy and satisfied. The key squared is, again, not zero, so that's the important information. And it's, yeah, the difference between observed and expected is higher than zero. So there is some difference. So the observed data, our data is drifting away, is far away from what we would expect by chance again. So there is a strong association. There is no, yeah. And what we didn't see before was the degree of freedom. Yeah, but this is clear that in a 2x2 matrix is only the degree of freedom is always 1. So yeah. Is this clear? Everything is fine. Any more questions before we wrap it up?
Maybe one small thing to add over here, like when we learned about the chi-square test, we kept saying about observed value and expected frequencies, right? So
Yeah.
one thing to keep in mind here is that whatever was in your question, like the number of satisfied people, not satisfied, whatever, that is your observed value. These are all your like everything that is in this freelance people, salary group people, like that is observed values. But you're comparing it with the expected. Now, how do you get the expected is a crucial question sometimes, because of course you have R that does the background work for you, but sometimes to understand it, it makes it clearer. So to get the expected values, you can calculate it. Like just looking at this problem, you can calculate that. So 30 are satisfied in the freelance group and 40 are satisfied in the salary group. So that is a total of 70, right? And there's 20 plus another 10. So that's 30 people who are not satisfied and 70 people who are satisfied, right? And with that, so that would be your observed value. So, sorry, your expected value. So if you think about it, you can say that, how do I put it? Out of the total 100, you have 70 people who are satisfied and 30 people who are not satisfied. And using that, so you can use a 70 over 100, so that's a 0.7, the value, multiply it with the 30 who are satisfied, and the value that you get out of it would be your expected values. So technically, if you multiply this and have your numbers, that's exactly what the chi-square test, the code is doing, the program is doing behind it. So yeah.
Yes, exactly. That was a very good point of having also in this case the numbers were like also around
Rounded off.
yes, exactly. And you can have this, 70% are satisfied. You can also use this as like always think how the
Yeah.
R is running things in the back.
Yeah.
Very nice.
Any more questions? Thank you.
Great. I hope you learned a lot of things today.